Hello guys, welcome back to another exciting video. In one of our previous videos, we explored the working of SEPIC converters with its waveforms. But this time, we are taking it up a notch. We are going to see the design of a SEPIC converter, witness its real-life working, and even conduct some actual tests on it. And all of these things will be powered by LM5157 application-specific IC from Texas Instruments. So let's start. Now for those of you who already know the ins and outs of SEPIC converters, feel free to jump ahead to this timestamp. But for all of you noobs out there, no shame in that, let's take a quick look at the circuit and working of a SEPIC converter. This is how a SEPIC converter looks like, which stands for single-ended primary inductor converter. We provide a PWM signal to the gate of this MOSFET Q1, which controls the working of this converter. Easy, right? Now, let's break down the converter's operation into different steps. When the active switch is turned on and when it's turned off. Before we go ahead, there's an important rule to remember about the inductors. They don't like sudden changes in the current. First up, when we turn on the input supply, the input capacitance charges up to Vin. But thanks to the series capacitor CB, the pure DC is blocked in the subsequent branch, which makes the circuit open. And guess what? No output voltage in this cycle. Now, Q1 is turned on. The input capacitance gets discharged by charging the inductor with a specific polarity. It charges up to the peak current while the rest of the circuit remains unchanged. After that, we turn off Q1. The input capacitance charges up again. Now, flyback voltage induces inside the inductor, causing its polarity to reverse. Now the voltage across Q1 becomes flyback voltage plus input voltage, and capacitor CP starts charging. Since this voltage isn't purely DC, current flows through the capacitor, making the diode even forward biased. As a result, we get the required output voltage and load current. Now, we switch on this MOSFET again. L1A starts charging due to the input capacitor, while L1B charges via CP. Due to CP's discharge, the diode becomes reverse biased and the load condition is satisfied by the output capacitor. Lastly, when the switch is turned off, L1A and L1B charge the coupling capacitor and output capacitor respectively and provide the output. These states keep repeating to regulate the output voltage. Well, it is a step up and step down converter, which is similar to buck boost converter, and that depends on the duty cycle of the converter. By the way, we can use a coupled inductor instead of two separate inductors. Yeah, this reduces board space and minimizes the noise. Pretty cool, right? This type of converter is called the constant voltage DC to DC converter, where the output voltage remains constant regardless of the input voltage. Alright, now we have mastered the power converter topology. Let's dive how we can control the circuit and regulate the output. Instead of getting into complex calculations and control logic, we have a better solution such as application-specific ICs like LM5157 from TI. It is very easy to design DC to DC converter using ASICs. All we need are some basic calculations, and in this case, we won't even need those. Trust me, it gets better. We select a few passive components, connect them to the ASIC, and voila. You have designed your own SEPIC converter according to your requirements. But wait, there's more. These ASICs offer additional advantages like undervoltage protection, overcurrent protection, overvoltage protection, and overtemperature protection. Even my health insurance doesn't give these many protections. Now, let's talk about the LM5157 IC for a moment. This bad boy operates within the voltage range of 2.9 volts to 45 volts, with a switching frequency of up to 2.2 MHz. It has an excellent efficiency and even comes with an internal MOSFET, eliminating the hassle of adding external one. Plus, it can deliver up to 6.5 amperes of output current. And guess what? It even has an optional external clock synchronization feature and a fantastic feedback reference with 1% accuracy. Oh, and let's not forget about the power good indicator. It comes super handy. Now, let's break down the functionality of each pin on this IC. We'll start with pin 3, which is a bias pin. It supplies the power to the IC's internal circuits. Right after that, we have the VCC pin, which is the output of an internal regulator, typically 5 volts. And check out the pin number 12. It's the internal FET or active switch in the SEPIC converter design. These pins, 8FB, which is feedback, and 9COM, short form for slope compensation, handle the vital task of providing the regulation based on the output voltage and current requirements. The FB pin takes the feedback from the output voltage via a resistor-based voltage divider, and this feedback is compared to a reference signal in the error amplifier. The output of the amplifier goes to a comparator, which compares it to the current flowing through the internal FET. This clever mechanism allows the IC to detect and control overcurrent shutdown. Well, the different applications will have different load currents, right? And that's where the COM pin steps in. By connecting external resistors and capacitors, we can adjust the error amplifier's gain where this overcurrent detection can be programmed. Oh, and there is one more input to the error amplifier, which is pin number 10, the SS pin. It's a soft start feature ensuring a smooth and gentle power-up sequence. This gradual startup helps the converter reach its steady state operating point, reducing the startup stress and surge. Well, this feedback circuitry I mentioned earlier needs to work in synchronization, and for that it requires an internal clock generator. And guess what? The LM5157 IC has a switching frequency of up to 2.2 MHz. We can select the appropriate switching frequency with RT pin when we hook up a resistor to it with respect to ground. And before I forget, there is a power good indicator too. It's an open drain output that goes low when the power supply is off, giving other circuits in the system about the health of this power supply. We just need to provide a pull-up resistor to it and give the signal for indication. There is one more pin that's a jack of all trades, which is this. This versatile pin combines under voltage lockout and enable functionalities. And they both have different voltage levels. To turn on this IC, voltage applied to this pin should be higher than both of these voltages. During turn on, if the input voltage starts from 0, the enable voltage comes first, followed the under voltage lockout. If the voltage applied to this pin falls below the under voltage threshold, the IC will go into under voltage mode and it won't start. But that's not all. This pin can also be used for sync, which means external clock synchronization. Instead of relying on internal frequency, you can provide an external clock to keep things in perfect harmony. Well, we are almost at the finish line. Just a few more pins to go. Next up, we have the power ground and analog ground pins, ensuring the proper grounding for analog circuits. And finally, we reach the mode pin. This little guy takes care of hiccup mode protection and spread spectrum. Interesting, right? Well, let me know in the comment section if you want to know details about that. We'll try to cover it in next videos. Now, let's shift gears a bit and design a SEPIC converter that delivers constant 12 volts output and supplies the load current of 1 ampere. Talk about versatility. We'll design this converter such that its input voltage range would be 4 volts to 32 volts. This baby's got you covered. Now you'll think that I have to do all of those components calculation and it will be boring. Well, here's the best part. TI provides a handy calculator to reduce that effort. No need to grab pen and paper, just input your desired specs and the calculator does the heavy lifting. Let's see how to use it. First is the minimum, maximum and nominal input voltage, which can be fed to the converter. Output voltage and current requirement is this. Then it will guide us through the selecting of the right inductor value, capacitor selection, output capacitor selection, soft start considerations, under voltage lockout calculations, loop compensation, and finally diode selection. Once you have all the calculations sorted out, you'll have a clear idea of which components you need to bring your circuit to life. And that's where this evaluation module from TI comes into play. It's specifically designed with the same specs that we designed right now. It features the LM5157 IC itself, along with input capacitors, output capacitors, a Schottky diode, and a coupled inductor, all packed onto this tiny board. Now it's time to witness the circuit in action. We'll connect our input DC power supply and turn on the oscilloscope. And don't forget, I have connected an electric load over here, which will sink all of the power from this power supply and will get the optimum results. Now let's check the output voltage. If you see on this electronic load, it is 12 volts and taking the current up to 1 amperes. Now let's check the switching frequency of this power converter. I have connected the probe to test point 6 of this circuit. And I'll turn on the load again, and the switching frequency is around 2.08 MHz. But let's not stop there. Let's put this converter to the test and check some important parameters. First up, we'll explore the output voltage regulation with respect to change in the input voltage. For that, I'll connect the probes of DSO to input and output and check the waveforms of it. Now if you look at here, the first cursor is the input voltage and the second cursor is the output voltage. Here you can check the input voltage and here you can check the magnitude of the output voltage. Now I'm turning on the load again. So right now the input voltage is 7 volts. I'll go down to 4 volts, which was our original design. Still, if you see, the output voltage is 12 volts. Now if I change the voltage from 5, 6, 7, 8, 10, 11, 12, all the way up to, let's say, 30 volts, still if you see, the output voltage is constant 12 volts. That's how we test the output voltage regulation of a DC to DC converter. This output voltage will become constant because the duty cycle adapts according to the requirement. During this time, the input current requirement for the converter also changes. Now, let's examine the output voltage regulation when faced with varying load currents. I'll take the load requirements now. Here on this load, it shows the output voltage and output current. Now I am changing the load resistance so that the output current will change. So as the current is decreasing, still if you see the output voltage, it's constant. If I go all the way down to even, let's say, 250 or 260 milliamperes, still the output voltage is constant. And that's how we also check the output voltage regulation with respect to change in load current. Phew, that was quite a ride. Well, this is how you can design a SEPIC converter using TI's LM5157 IC. We can use the SEPIC converter in various applications, from power supplies and LED drivers to automotive systems. You can make a flyback converter or even a boost converter from this IC. So, what do you think? Would you like to see some more design videos like this? If yes, let me know in the comment section below. And don't forget to hit that subscribe button for more exciting videos. I will see you in the next amazing video. Till then, stay hungry, stay foolish.